My name is Kelly Cline. I have the great honor of teaching here at Carroll College. I get to teach all the most fun courses in math and physics and astronomy and stuff like this. I have the privilege of giving this, which is part of an ongoing series of public presentations about fun, cool, exciting discoveries in science, mathematics, the universe in general. Today's presentation is about the discovery of gravitational waves. This is one of the biggest discoveries of the last few years. I guarantee within the next couple of years, Nobel Prizes will be handed out for this great discovery. So thank you for your coming, and I hope you enjoyed tonight's presentation. Good. All right. So there's a little bit of a computer visualization of what these gravitational waves are. Here's a quick summary. I always got to do the history behind things because I love that. We'll talk about the various theories of gravity throughout history, Aristotle, Isaac Newton, and then this one really gets started with Albert Einstein's theory of gravity, and it is from that, from the mathematics of Albert Einstein's theory, that we get this idea that there can be waves of gravity propagating, moving through space. We'll talk about the first real evidence that these things exist. That was from the 1970s. It was kind of indirect, but Nobel Prizes were given. And then we got to talk about the LIGO Observatory, an absolutely heroic enterprise where we got 2 laboratories down in Louisiana, up in Washington State. The whole thing was just an absolute push the edge of technology. Let's see what's possible. Let's see what we can do. And amazingly enough, it worked. The discovery was made, and now we're beginning to use these discoveries in order to learn more about our universe, which is the whole point of the whole thing. So start at the beginning. I always love to start with ancient Greece because that's when so much of our civilization starts, where we get these ideas of democracy and freedom, theaters and playwriting, philosophy, history, mathematics, sculpture, architecture, and of course science, where we see groups of people debating, arguing, discussing together based on the idea that our universe has rational, logical laws, and we can figure them out using careful observation of the world around us and using mathematics, and then that will tell us how things work in our universe. And that's an amazing thing. We got to start with this fine gentleman here. This is Aristotle, often considered the father of science. He asked a lot of wonderful questions. He did all sorts of glorious things. He was the first person we really know of who really wrote seriously about the question of why do things move? What causes motion? That's the root question of the science of physics. He wrote books about all sorts of things. He was all over the place. He wrote books about biology and zoology. I hear his botany is very good. I don't know about that. But basically his big thing was he said that using careful observation of the universe, we can learn about the universe and how it works. That was in contrast to many of the most influential philosophers of ancient Greece. There were philosophers like Plato who argued that you shouldn't believe your eyes and your senses, and that showed you nothing but like shadows on the wall of a cave, and that's not real, and no, you can only learn about things by thinking about them. Aristotle, his student, said, no, we can learn by observing carefully. And when you observe carefully with your eyes and you double check it a few times, no, they're not going to lie to you. So he did a lot of really foundational stuff. On the other hand, when I look at Aristotle's physics, he didn't use math. It's all qualitative. It's all, just words and ideas. And he really didn't perform any systematic experiments to put his ideas to the test. Those are essential things if we're going to do any serious science. Aristotle's theory of gravity, the first great theory of gravity in history we know about, is that, his old physics is based on the idea that all our world is made of 4 elements, earth, air, fire, and water, and that gravity is the force that pulls the heavy elements toward the center of the universe. So that's where the water and the earth go. And then gravity is balanced by what Aristotle called the force of levity, which causes the light elements, the fire and the air to move up. And then beyond that, you have the ether up in the heavens. And that's why everything in the heavens moves in perfect circles. That was Aristotle's theory of gravity. His theory of motion is said that basically objects move only when forces act on them, and a constant force will cause a constant steady motion. And even as he said that, he also knew that this had some problems with it. I mean, if I have a falling object, that's a constant steady force of gravity, and yet things get faster when you drop them. There were a number of things. If I throw, he gives the example, if I throw a spear, well, he knew that the spear kept going, even though I'm not pushing it on it anymore. It keeps going. And so then he ties himself into knots, writing about what that could be and how that could work, and comes up with some ideas about that. But he knows there's some challenges to this. Let's talk about this one. We'll fast forward in history by 2,000 years. This is Galileo holding his telescope there, as well he should. Galileo's work in astronomy and with telescopes is wonderful, and his work in physics was at least as important. By doing he did these great experiments rolling these balls down ramps, and Galileo figured out how gravity really affects things. No, gravity causes things to increase its speed at a constant rate, causes things to accelerate. That's what forces do. Forces make things get faster and faster and faster. And best of all, Galileo came up with a mathematical law of that. He figured out how to mathematically predict and calculate how far the ball is going to go after a certain amount of time as it goes faster and faster. Now we see the real beginnings of physics. He's doing experiments. He's using equations. He's putting his equations to the test by gathering more data. This is the process. This is the heart and soul of things. Beyond Galileo, we have to introduce my man Isaac Newton there. I don't think that's a real photo of him. But anyway, so he's late in life, he actually told the apple story it was his niece or something like that. He told the story, he was out on the farm and observing apples falling from trees, and he's pondering about the mystery of what holds the moon in its orbit. And he has this great leap where he suggests that maybe the force that holds the moon in its orbit around the Earth is the same force that pulls apples down to the Earth. That was extraordinary. That was mind-boggling. Up until that point, most people had tried to come up with some different force to explain the heavens than what we've got here on Earth. Newton proposes, no, that there's one force of gravity that pervades the universe, and it attracts everything in the universe to everything else. Right now, there is a force of gravity pulling my right hand toward my left hand. I can't feel it because it's really small, because their masses are small. You need like an Earth's mass worth of things for it to be really substantial. But this is Newton's view of gravity, utterly different. Aristotle, well, gravity pulls heavy things toward the center of the Earth, the center of the universe. Newton says, no, gravity pulls everything toward everything else. But how does it get from here to there? He gives this wonderful, beautiful law of gravity. He figures out that, okay, we've got a formula. He describes this works. He does the calculation, shows this explains why the planets orbit in ellipses. It's beautiful, it's lovely, it's glorious. And Newton was disturbed by the question of, well, how does gravity get from the sun to the Earth? How does gravity get from the Earth to the moon? How does that work? Here's, in a letter, he wrote this. He said, that one body may act upon another at a distance through a vacuum without the mediation of anything else, by and through which their action and force may be conveyed from one to the other, is to me so great an absurdity that I believe no man who is in philosophic matters a competent faculty of thinking could ever fall into it. But of course, that's his theory. That's his whole bit there, that he did, that absolutely one body acts on the other one. It's a vacuum of space between the Earth and the moon, between the Earth and the sun. And it drove him nuts. He in another letter, he referred to this action at a distance as spooky. He could totally understand how if I'm here and I touch this, I can exert a force on it. But how does my gravity get from here to there? How does the gravity of the sun get out to Jupiter? And there's just empty space between the two. Drove him nuts. And nobody could understand that until Albert Einstein. That's really what happened. After Newton, people said, well, it doesn't matter how gravity gets from here to there. Newton still didn't like that idea. But after that, no, they said it's irrelevant. The equation works. Deal with it. And for a long time, people thought gravity was done. Newton, the great genius, had figured out gravity, and that was it. End of gravity. You go work on electricity and magnetism. Gravity's finished. And then Einstein comes up with a very different theory of gravity. He showed, and it's not that they give totally different results. He showed that Newton's equation is a beautiful, wonderful, excellent approximation to something deeper, and that in almost all situations, the difference between Einstein's equations and Newton's equations is so tiny you could never even know. But Einstein's general theory of relativity proposes something different. He proposes that gravity is a bending of the fabric of space itself. That space itself is not just a blank canvas on which things are set, but actually, even if space is completely empty, there can be information in it. There can be ripples in it. It can be stretched and pulled. And that space forms a fabric, the space-time continuum. And it is the bending of space which transmits the force of gravity from the sun to the Earth to the moon, from Jupiter to its moons. That's an amazing idea, and this changes our idea of gravity. Now, gravity isn't just, okay, there's an equation for it, but no, there's a process behind it. And so as a result, Einstein's equations tells us that gravity takes time to get from here to there. Gravity travels at the speed of light, which is fast but not infinite. So it takes about 8 minutes for light to get from the sun to the earth. And Einstein's equations say it also takes about 8 minutes for gravity to get from the sun to the earth. If I waved a magic wand and made the sun vanish and go away, what I would find is that for 8 minutes we would continue to receive the sun's light, because it still takes 8 minutes to get here from there. And for 8 minutes the earth would continue in its orbit because it was still feeling gravity from the sun. And then after 8 minutes the light would run out and the gravity would run out, it would get cold, and the earth would go off into space. And that would be really cool, except we would die. All right. Now the sun is not making gravity waves. It's pretty much just sitting there, as it slowly orbits around our galaxy. So its gravitational field is fairly steady. Einstein's equations tell us that you can make gravity waves not when you're just pretty much sitting still or moving at a steady sort of thing, but no, you need to have something changing its gravitational field. You need something accelerating, moving, changing, orbiting, something like that. And if you're more massive, as you move around quicker, that's going to give stronger gravity waves. And if you're less massive, that will not be so much. The sun's gravity is fairly steady, so it is not giving off significant gravity waves. On the other hand, if I have two stars orbiting around each other, now they're going to make waves because they're accelerating, they're in motion. We've got our two stars there orbiting around their common center of mass. The bigger ones closer to the center, the farther ones farther away from that. And as they orbit around each other, that's something which would give off gravity waves. That's something which is actually going to send ripples out into the space-time continuum, moving away from each other as a result of that. And then the more massive those stars are, the stronger their gravity is. Aha! That's going to make the gravity waves stronger. And turns out gravity waves are pretty weak things. We'll talk about exactly how weak in a minute. So we need the most massive stars we can find in order to make significant gravity waves. Now, normal stars are not, our sun is of moderate mass as far as stars go, but there are other things with stronger forces of gravity. For instance, we have neutron stars. A neutron star, it's basically just a ball of neutrons. It's not even made of atoms anymore. It's the crushed leftover remnant of the core of a star that went supernova and exploded. It's just a few miles across, but as massive as the sun, and so it has an enormous gravitational field. A black hole. There's another idea that came out of Einstein's general theory of relativity, that I can have an object with gravity so strong that nothing, not even light itself, could escape from it. That would be something with an enormous gravitational field. So if I had a black hole moving around, that could give off strong gravitational fields. Another idea is the supernova explosion itself. If I have a huge, giant, massive star that burns through all of its fuel and then its core goes unstable and collapses into a neutron star, that violent event, because we've suddenly got a big change in a bunch of massive things moving quickly, that could cause gravitational waves. But here's the problem. When we do the math, when we actually calculate how strong would these gravitational waves be, what would it take to detect them, they are amazingly weak. It is absolutely, well, first of all these sources are ridiculously different. They're distant. They're at least thousands and maybe millions or billions of light years away from us. The typical, when you figure, okay, you got black holes this distance, how far much are they going to bend space? When we do the math on this, according to Einstein's equations, these sources I've been talking to you about would be able to bend space on something on the order of 1 part in 10 to the 21st, 1 part in a hexillion, which is really, really ridiculously small. Einstein himself wrote about this and said, it's some lovely math, but I doubt anyone will ever be able to detect that. How could anyone measure or detect or verify a stretching or a squashing of space that's so small, so infinitesimal, 1 part in a hexillion, 1 part in 10 to the 21st? How would anyone ever have any instruments which could detect a motion that tiny? Here's the other thing we need to know about gravity waves. Gravity waves, like all waves, carry energy. If I throw a rock into the lake and I watch those ripples go away from that, well, the energy came from the rock. The rock, when it hits the lake, that delivers some energy, and then the waves carry the energy away. When I'm speaking right now, those sound waves going from my vocal cords all the way to your ears, those carry energy. Energy that I'm generating right now is then received by your ears, and that's how it works. Waves work like that. It's light waves, radio waves, right? The light bulb gives off energy as in terms of light waves. And so gravitational waves, like all waves, carry energy. And this tells me something very important. Suppose I've got two stars orbiting around each other. I told you two stars orbiting around each other are going to give off gravitational waves. That means that they are losing energy all the time, that those gravitational waves are carrying energy away from them. And it is the energy of motion of those two stars orbiting around each other which prevents gravity from just bringing them together and smashing them in together and merging them into one star. So since they're losing energy every time they orbit around each other, since those gravity waves are carrying energy away from them, what that means is those two stars will slowly spiral in closer and closer and closer to each other as they lose more and more energy. Gravity waves carry energy. The energy comes from the energy of motion of the orbiting objects, and so as a result, since they have less and less energy of motion, they're going to get closer and closer and closer and closer until finally they would collide. Now, a typical two stars orbiting around each other, if they're about the mass of our sun and they're a few million miles away from each other, they can orbit like this until practically the whole age of the universe, and that's fine. That's not a problem. But if I've got something like neutron stars or black holes, now that's an interesting thing. If I put two black holes into Einstein's equations and I see, well, what happens? Well, they're going to orbit around each other, and as they get, and these will give off a lot of gravitational waves, and then over time, over millions and billions of years, these could come closer and closer and closer together until finally Einstein's equations say that those two black holes should collide together and merge into one big giant black hole. That's an amazing calculation. That was done for the first time in the 1920s when people calculated what would happen with that in an approximate sense. And this would be a big source of gravitational waves, but again, very tiny stuff. Absolutely ridiculously small things. These ripples in space are really, really, really small. Even the most intense, violent events we can imagine would create the tiniest ripples in space. So, what was the first evidence of gravitational waves? It came from these two fine gentlemen, Russell Hulse and Joseph Taylor, University of Massachusetts at Amherst. They were using the Arecibo radio telescope. So it's down here in Puerto Rico. It's kind of a whole valley that's filled in with this great, big, amazing, powerful radio telescope there. And they've discovered a new pulsar. Now, a pulsar is a type of neutron star. So it's a ball of neutrons. It's not made of atoms anymore. Just no protons, no electrons, just neutrons, all held together by gravity in a tiny ball just a few miles across. And we find a lot of neutron stars are spinning really fast, about once a second, and they have a very strong magnetic field. And so as they spin around, they give off pulses of radio waves. And what they found is they studied this neutron star, and they measured its pulses, and what they found was that, well, this pulsar, this one's a fast one, it spins around 17 times every second, absolutely screaming fast. But they also found the pulses vary slightly. They come a little bit faster and a little bit slower, and a little faster and a little slower, in a cycle lasting, 7-8 hours just about. So if you watch this pulsar, now most pulsars are just absolute, they're nature's clocks. They are very, very, very regular. They are almost as regular as the most accurate atomic clocks we can make here on Earth. So they are very regular, but this one varies in a cycle. It goes a little faster, a little slower every 8 hours or so. And they realized this means the pulsar is orbiting around another neutron star, which isn't giving off pulses. And so you got two stars orbiting around each other. And so when it's moving towards us, the pulses come faster. And when it's moving away from us, the pulses come slower. And so that's fine. And you have two neutron stars orbiting around each other. And they figured their masses, they're both about 40% more massive than our sun. And they're orbiting very, very close together. And Einstein's equations tell us those two neutron stars orbiting around each other must be giving off gravity waves. And Einstein's equations tell us that the energy those gravity waves are spreading out into the universe come from the motion of those neutron stars, so they should be spiraling closer and closer together. And as they get closer together, since they have less energy with which to fight the force of gravity, they should orbit faster and faster and faster. So they start out far away, orbiting relatively slowly, and then over time they get closer and closer and closer together as they lose more and more and more energy. And so as a result, we should be able to measure this. And they calculate, well, okay, the star is 40% more massive than the sun. This is their orbit. They orbit every 7-8 hours. Should we be able to measure it? And the answer was yes. They should be able to measure a very slow decrease in the orbital period. That orbital period, that 7.75 hours, should get smaller by 76.5 microseconds per year. Now, a microsecond is a long time. This is a very short time. But you know what? We have instruments that can do that. We have computers. We have glorious, wonderful electronics that can measure we have stuff that can measure nanoseconds, microseconds. That's an eternity to us. We can do this. So they did. They very, very carefully measured that 7.75-hour orbital period of those, and the pulses of the neutron star were really helpful with setting that up. And what they found is it works. They found that that period that got slower, it got faster. They were orbiting faster and faster by exactly the right rate. They measured the first few data points there. Over the last few years, we found that those stars are getting closer and closer and closer together, exactly following this curve, which is predicted by general relativity, by Einstein's equations. Absolutely amazing. They did the calculation, they made the measurement, and bang, it hit the numbers on the nose. Now, this is the heart and soul of the scientific process. I mean, we can have all these ideas about what gravity is and bending space, and it's lovely and it's beautiful and it's wonderful geometry. But the science where the rubber meets the road is when I actually calculate a specific number. And I say 76.5 microseconds every year is the amount that this should change by. And then we measure it. They go to the great big Arecibo telescope. They measure this over a period of a couple of years, and the numbers match. The numbers that they get out of the radio telescope and the numbers that came out of those beautiful, lovely equations are the same numbers. Now, what are the odds we're going to hit that on the nose by chance? That's a very unlikely thing. That's the heart and soul of the scientific process. When those two sorts of numbers, the theoretical numbers and then the actual measured numbers, when those are the same numbers, that means maybe we know what we're talking about. And that means maybe somebody's going to win a Nobel Prize. There's the same guys there in a rather lighter moment than I showed earlier. As a result, this is beautiful evidence of gravitational waves. Not direct evidence, they still haven't detected them, but as a result, from their work in the 1970s, in 1993, they won the Nobel Prize. And then the big question is, okay, now we have great indirect evidence that these gravity waves exist. Can we see a gravity wave itself directly? And that's the trick. In order to do this, well, what do gravity waves do? Well, they stretch and squash space itself so that the space between here and here will get smaller and bigger and smaller and bigger. And again, it's 1 part in a hexillion. Small stuff. So how do we do this? We build LIGO. The idea behind this was dreamed up by Kip Thorne down at Caltech and some other guys up at MIT back in the 1980s. They originally started out kind of competing against each other. They put 2 different proposals into the National Science Foundation, and they called them in and said, gentlemen, let's work together on this. And so they did. And so LIGO stands for the Laser Interferometer Gravitational Wave Observatory, because they figured that using lasers, they should be able to measure that 1 part in a hexillion. There are 2 sites, Hanford, Washington, and then in Livingston, Louisiana. Both sites have these 2 big long arms that are 4 kilometers, about 3 miles long. And then there's this big powerful laser system that bounces this way and bounces that way and then compares the 2 distances of these things and then can detect that tiny, tiny stretch or squash in the lengths of these arms. So this one's the Hanford site. You can tell by the lovely arid eastern Washington sort of setting there. And then here's the Livingston site. Okay, Louisiana, you see all the trees and stuff going along there. The big proposal to LIGO was proposed in 1989, approved the following year, ground broken in 1994. The observatory began operation in 2001. By now, the total cost has been $620 million. This is the biggest and most ambitious thing ever funded by the National Science Foundation. Absolutely enormous. So how do you use lasers to measure distances? Well, here's a little diagram. You take your laser beam here, and then what you do is you take your laser beam and you split it in 2. You send it through a mirror which only reflects about half the light, and so about half the light is sent off in this direction, and then half the light is sent off in this direction, and this goes 3 miles this way and comes back, and this goes 3 miles that way and comes back. And when those 2, so they bounce back and forth a whole bunch of times, about 75 times each, and then after bouncing back and forth all these times, the 2 beams are recombined and you detect them there. And the idea is that if these lengths are perfectly fixed and constant, those 2 laser beams will cancel each other out completely. Because laser light is made of waves. Waves have peaks and troughs. It goes up, it comes down. It goes up, it comes down. It goes down, it comes up. And they tune these just perfectly so that the waves coming in from one arm and the waves coming in from the other arm will cancel each other out, as long as the distances remain constant. If the distances change, if one of them stretches or is squashed in one direction or the other, then they're not going to cancel each other out, and so they've got a detector there. It's waiting there, waiting to detect a tiniest flicker of light. If it can detect any light at all, well, something happens. Maybe a gravitational wave, or maybe something of any sort. There's a lot of different things they can do this. So this is how it works. It bounces the light beam back and forth. In both sites they've got one of these. They tune it until the light waves cancel out perfectly, and then they wait to see if anything causes a flicker of light to appear. The photodetector checks for any signal 16,000 times every second, which is rather extraordinary. And the frequencies it's listening to are the same sorts of things we can hear. Now, our ears are turned to vibrations in the air, not vibrations in gravity. But, you know, these are also sound waves. These are also the same frequency as sound waves that, you know, my voice and music and all those sorts of things are talking about. They're not ridiculous things. Now, the biggest problem is noise. I mean, gravity waves are not the only thing that are going to shake things up. There are also earthquakes. The site up in Hanford, they can detect waves at sea, even though they're hundreds of miles inland. Strong winds, even human activity. Down at the Livingston site in Louisiana, it's right in the middle of this tree farm. And turns out there's chainsaws, there's trees falling over. That's a problem. This is one reason why they need two sites. If I get a signal here and I also get a signal there a couple thousand miles away, probably we've got something. But first, they need to filter the noise out, all this other stuff, the cars and trucks and people hitting telephone poles and minor earthquakes and all this stuff so what they do is they have to eliminate all this noise. So first of all, there's this passive system. These are the mirrors right there. They're hung from these loops of steel piano wire attached to a steel cage, and then it's on a table that has stacks of stiff springs and circular steel plates that they eliminate all the high frequency noise. And they tried that, and they found that the site in Livingston needed more. You got this tree farm. They're raising all the pines here for paper, and so there's all this low frequency stuff. And so they needed more than that. At first, they could only run at night when all the guys are home and everybody's at when that wasn't good enough. So they needed an actual active system to counteract all the sound waves and all the vibrations of the Earth. So they have what they call the HEPI, Hydraulic External Pre-Isolator, which, first of all, they have ridiculously accurate seismometers, the same things that measure, you know, earthquakes and stuff. And then they have a hydraulic system which moves in the opposite direction, so cancels them out exactly. It's like those noise-canceling out earphones that some people use. So it moves very slowly, but it quieted the loggers so they could work during the daytime, and really, really made an amazing difference. Their first big science runs were between 2002 and 2010, big science runs where they take a few weeks of data, analyze it carefully, a couple months of data, and they tried to make things more and more and more sensitive. Nothing. They spent years and years analyzing, looking for data, hoping for that Nobel Prize. No, they were unable to detect anything. So they went back to the National Science Foundation. They asked for another $200 million in order to build things better. Well, you know, come on, this is important. This is cool stuff here. So they had what they souped it up and created what they called Advanced LIGO, originally called LIGO 2, where they needed to filter out more noise. It's all about all that garbage and all that sort of thing. They spent 5 years, 4 or 5 years between 2010 2015, bigger mirrors, more powerful lasers, putting a HEPI system in at Hanford site as well, allowing them to see 10 times more stuff, 10 times stuff farther away than the first LIGO. And the idea was that here's a graph that shows, okay, here's the strength of the signals here, and then here's the frequency of the signals. And the original LIGO could find this stuff, and they're like, if we can soup all this up, we can find even weaker signals, lower things, and then lower frequencies. And there's all sorts of interesting things down here they expected to see. And so that's what they did. They installed that, got things in there in 2015. And on September 14th, 2015, they hadn't even started a science run yet, but they had everything working. Both systems in Livingston and Hanford were working. They were still in engineering mode, still debugging the system, clearing things out, when they got a signal. On September 14th, 2015, they were going to start the official research data 4 days later, but they picked up a signal that lasted for just 0.2 seconds. And when they first picked it up, everybody assumed it was a test of the system, that, you know, somebody had artificially put some in there just to see if we could actually detect something in there. But it was not an artificial sort of thing. The blue line here is what they got from the Livingston site down in Louisiana. The pink line here, that's the Hanford site. And they both picked up a signal at almost exactly the same time. So here's the data. the signal from Hanford, the signal from Livingston, and then down here, this is what Einstein's equations, if we numerically solve them on a computer for exactly what we would expect from these orbiting objects, this is what we would see. And you notice that we could get the waves, and then they get faster and faster and faster, and then they stop. That's a merger. And so this is the theoretical calculations, and that just beautifully matches the data here. The data is rougher and noisier, but when I subtract that off of the data, I just get random noise left. Here's my frequency versus time plot. I can see it getting faster and faster and faster, and then stopping. This is what it should look like. This is the signal they were desperately hoping to find. This is the whole dream. Ever since the 1980s, when they dreamed about this, this was the signal they thought they might be able to see. Two black holes merging, orbiting faster and faster and faster and faster, and then they splash into each other, give off an enormous amount of gravity waves. Let me tell you how much they were. So based on those frequencies, they can tell that the two black holes must have had masses about 35 solar masses, 35 times the mass of the sun, and 30 solar masses, 30 times the mass of the sun. So we got two different black holes, each one with 30 and 35 times the mass of the sun. And then as a result, as they get closer together, then they merge and they create a black hole with 62 solar masses. Now, you'll notice that 35 plus 30 should be 65. Because Einstein's equations tell us that when two black holes come together and splash into each other and create a giant, powerful uber black hole, an enormous amount of their mass should be turned into energy of gravitational waves. So as a result, those 3 solar masses worth of energy were turned into gravitational waves by Einstein's equation, E equals mc squared. Einstein's equation tells us that mass can be turned into energy, energy can be turned into mass, and in this case, 3 times the mass of the sun was turned into energy all at once. This would be what you got if you got a sun and a half of matter and a sun and a half of antimatter and put them together. Now that's one fun weekend right there. This is extraordinary. This is, the sunlight that our sun gives off on a daily basis is lovely. And that's on the order of less than 1/trillionth of a solar mass per billion years. This is an extraordinary amount of energy, and that's why we're able to detect it, because it's huge. Everybody wants to know, where was it? Well, the frequencies of the orbits and how fast they got faster and faster, that tells us the masses of the black holes involved. From there, we can calculate the total energy released, and then we calculate how much of a wiggle did we notice here on Earth. Very, very small. And so we can calculate that this must have taken place between 1 and 2 billion light years away from us. So this is an incredibly distant thing. This is not in our neck of this is not the Milky Way galaxy at all. Milky Way is only 100,000 light years across. We're not talking, Andromeda, other nearby galaxies, those are a few million light years away. This is billions. This is a very, very, very distant object. We can kind of tell a little bit about where it came from because Livingston saw the signal 7 milliseconds before Hanford. So that means, well, this is farther south. So it must have been somewhere in the southern hemisphere skies. Probably not a point in the sky we can see from here in Helena, but beyond that, it's very hard to tell. If we really wanted to pin down exactly where this was coming from, what we'd need is about a dozen LIGOs installed at different points all the way around the world. I talked to the National Science Foundation about this. They said they'd get back to me about the funding. We're lucky we got the 2. There we go. And here's the 2 signals put together, the signal from Hanford and the signal from Louisiana. You can see them interacting together faster and faster, and then splash, the 2 black holes come together. The first thing they did was they talked to ordinary astronomers, visible light astronomers, optical, radio, infrared, X-ray, all sorts of telescopes immediately started scanning that very large region in the sky to try to see if they could see anything unusual. Sometimes there's hot gas falling into black holes. Maybe we could see something when that happened. No such luck. But they looked for it. That would be really interesting. If we could ever find an optical counterpart to this where, we got a black hole merger here, and then, we can actually see how that's affecting the hot gas surrounding that, that would be incredible. That would be absolutely extraordinary. We would be able to learn a lot from that. Didn't find one this time. They will definitely keep looking for that sort of thing. So the data was found in September. And so the first thing you do is you double check and you measure and you test and you verify, and okay, these look like waves, and it was detected by both of them, and so they went through everything. They double checked, cross-checked everything. There's nothing more embarrassing, than holding the press conference and then having to hold the second press conference. So that's not as much fun. So they did. They put they locked this thing down good. Considering, I mean, the team of scientists and engineers involved in this, they've got an enormous staff of people. Lots of people knew about this. But the fact that they were able to keep this silent until it finally, until the big announcement, that speaks well of their team. They checked things for a couple of months. They submitted a paper to Physical Review Letters, which is one of the most big prestigious journals in physics. And they sent the letter. They expedited everything because everybody knew this is earth-shaking sorts of news. So they knew this is big stuff. They sent it out for peer review. They got it back within a couple of weeks, and so they were able to. It appeared in the February 12th issue of the Physical Review Letters. The paper itself, this kind of science, this kind of experimental big science, requires lots and lots of people. Even if you're just talking the physicists, the scientists themselves, there's a lot of people involved in this. Usually at the top of every paper you list all the authors, and in this case they listed B.P. Abbott et al., and then there's an asterisk, and it says the full list of authors is giving, at the end of the paper, and you flip to the end of the paper, and there's like 105 authors on this one. So lots and lots of people were involved in this. I think this is most scientific papers don't have over 100 authors, but everybody who invested in this got to be a co-author on this paper, and Abbott was listed first simply out of alphabetical order. Amazing stuff. They held the big press conference there, so the team behind it, Kip Thorne and the other guys who proposed this back in the 1980s are there, the head of the National Science Foundation. Big, extraordinary, amazing news. And meanwhile, before even the press conference itself, while they're still trying to get their paper through and everything, they got another signal. On December 26, 2015, the day after Christmas, another signal was found, a different signal, but again, another similar chirp was discovered. This one was weaker. It was not nearly as strong as that first one, but it lasted for a full second. It was a much longer signal. Hanford picked it up just 1.1 milliseconds after Livingston. And this is an interesting signal. You can see, in this case, we've got a full 27 orbits leading up to the merger. The other one has, depending on how you want to count it, maybe 7 or 8 orbits. We kind of count the last 7 or 8 orbits before these things splashed into each other. Now, why would that be? This is a weaker signal, and yet we were able to see it longer. This all has to do with the mass of the black holes involved. The other one was 30 and 35 solar mass black holes. Since they're so massive, they're going to give off such powerful gravitational waves, and so they're going to spiral into each other fairly quickly. They are only going to be close enough to give off detectable gravitational waves only, 0.2 seconds before the end. This was a system with less massive black holes. And so if they were spiraling towards each other more slowly, which is why we're able to see a full 27 orbits. The data I showed you before had a lot of noise filtered out. Here is here's the noise on top of it, and then the unfiltered stuff is in here. Now this is, as you can see, the noise is huge compared to the signal, but the fact that it lasted so long and it had so many regular, predictable cycles to it, that allows us to beat the noise. I mean, they've got these incredible systems to filter out all the vibrations, and yet still, there's an incredible amount of noise. When you're measuring 1 part in a hexillion, this happens. But the longer a more regular, predictable signal is, then when I use my beautiful methods of glorious statistics in order to attack that noise and to try to tease out the subtle, beautiful physics going on in there, if I've got longer signal, 5 times more data, it's easier to beat down the noise, and that's why they were able to find it. When we run the numbers on this one, we get about a similar distance, although it was coming from a different spot. Again, something about, in this case, about 1.4 billion light years, give or take half a billion years. What's half a billion light years between friends? When we run the numbers, it was from about, the 2 black holes were about 14.2 solar masses and 7.5 solar masses. So not 30 and 35, but still, these are still hombres here. They're going to come together. They orbit around faster and faster and faster. They splash. They create one giant uber black hole. And in this case, it has 20.8 solar masses. Einstein's equations then tell us, again, 1 solar mass, 1 entire solar mass is instantly transformed into energy of these gravitational waves. And that's how we're able to detect it and see that this actually exists. That's the heart and soul of things. And there was another signal too. If we go back, so those are those 2 signals. There was another signal that was found on October 12th. after the first one. The first big one was found on September 14th of 2015. That second one I was talking about, well, that's December 26th. There was a signal between those found on October 12th. It was weaker, and it looks beautiful. It's a lovely, beautiful signal. But when they attacked it with the statistics, that noise won, kind of. We can see it. We can see something there. But the standards for scientific publication are high. And so they want to get to a level where they can say that, no, there's only a tiny, tiny, tiny probability that you would see something just by random chance out of the noise, that the random noise would just happen to line up into this beautiful wiggly pattern. And when they did the calculations, they said, no, there's about a 5% chance you would see wiggles like this based on just random noise and nothing real. And so that one they couldn't publish. They put it up on their website and they said, okay, here's what we had. It doesn't meet the standards for scientific publication. We need to be able to take this to the bank. And since the statistical analysis wasn't as strong on that, they weren't able to do that. I still think it's probably real. I think most people do, but you can't be sure. If it's real, then that was a merger of a 23 solar mass black hole and a 13 solar mass black hole. But it just didn't quite meet the gold standard for data analysis. Too much noise. You can put the model in there, and that's lovely, but you got to have just a very, very small chance that you would see this just as a result of random noise conspiring against you. And they couldn't quite get to that level. So there it is. The second black hole was announced. The second black hole merger was announced in June of last year, and as a result, they've been picking up prizes right and left. This is huge. This is enormous. So the team, Ronald Drever, Rainier Weiss, and Kip Thorne, the team from MIT and Caltech that came up with this idea. They got the Special Breakthrough Prize in Fundamental Physics, the 2016 Shaw Prize, the 2016 Kavli Prize, the Gruber Prize in Cosmology. Everybody's waiting on the Nobel. It was not they didn't get the Nobel Prize last year. There was another group for some wonderful, interesting research as well. It's got to happen within the next couple of years. This is just so extraordinary. And this is the stuff the Nobel Prize Committee loves to reward. They're very, very big on experimental confirmations on big theoretical stuff. I mean, you can do theoretical work all career long, and it can be glorious, wonderful, amazing stuff. But without an experimental confirmation, you'll never win the Nobel Prize. This is why Stephen Hawking has never won the Nobel Prize. He's an amazing physicist. He's done just absolutely revolutionary stuff in terms of black hole theory and all this. But it's pretty theoretical, and probably it may be centuries before we can really put his stuff to the quantitative test. If somebody ever manages to confirm and test any of Stephen Hawking's great work with black holes or stuff like that, he'll win the Nobel Prize that year, or within a couple of years, but probably not. The Nobel Prize Committee is all about experimental confirmations and verifications of things, and so this is the stuff they love. These guys are going to Stockholm. So anyway, so what do we do next? I mean, what does this mean? What can we learn from this? Well, the first thing is, this is a proof of concept. This proves that, yes, gravitational waves are real and we can find them. We can find more than one of them. They tell us some things. They come from the sorts of sources that Einstein dreamed about years ago. They're actually real things and we can measure them. So that's great as far as it goes. And now we can, the National Science Foundation is great. They do some wonderful funding and I love them to pieces. Let's go to NASA next. Because the problem with these two sites in Hanford and Livingston is it's on the Earth. And then you've got all these other things on the Earth like earthquakes and wind and waves and people, for crying out loud. We need to get away from all these annoying sources of vibrations and the chainsaws and all that. You go to space and a whole nother level of things will open up. The fact that now we have shown that this can work on Earth, and it means you're going to be able to do at least 1,000,000 times better if we go to space. This is a beautiful proof of concept. One proposal which NASA looked at for a while, couple of years ago, was what they would call not LIGO, but LISA, Light Interferometer Space Antenna, where now instead of having these arms on the Earth and correcting, suspended on the piano wire and the springs and all that, forget about it. Send them out into space. Rather than make these things 3 miles away from each other, let's put them millions of miles away from each other. That will allow you to detect much weaker signals since you don't have all the interference. I mean, this would be extraordinary. Again, big project, but NASA likes big projects. They do big. That's their thing. LISA, when it was originally proposed about 15 years ago, they considered for a while and then cut some funding, and that's coming back. I mean, there are now several other laboratories on Earth trying to catch up with LIGO and detect gravitational waves. There's even one over in Italy, the Virgo lab, which was not functioning in September and December of 2015. So otherwise, they probably could have confirmed the LIGO signal. They're up and running now. There's another lab in Germany which is up to try to detect gravitational waves. India is trying to develop a great big one in partnership with the United States. There will be other ground-based gravitational wave observatories coming online, some of them right now, more trying to get more data out of this, but I really want to see what happens when we put gravitational wave detectors in space, because that's going to be able to detect a whole nother realm of stuff that we can't even begin to dream about finding from here on Earth. That will allow us to go into much lower frequencies and much lower, much weaker signals. This should be able to detect not just, two black holes splashing together and making a giant uber black hole. Instead, you can just have two black holes orbiting around each other. They might be 1 billion years away from a merger, and we should be able to find them. Neutron stars orbiting around each other, or even supernova explosions. That would be some really interesting thing. It's probably going to be a joint American-European project, something of that sort. That's the next move in this chess game. That's where it has to go from here. And I'm most interested, if there's one bit of data I want to see out of that. Okay, so we've confirmed that black holes can merge. That's great. I mean, this is the strongest evidence that black holes exist right there. What I really want to study are supernova explosions. When big giant stars run out of fuel and their cores go unstable and they collapse to create a neutron star or a black hole. That's one of the knottiest, the thorniest, the most difficult questions in the science of astrophysics. How does that work when you've got a big giant star, maybe 10, 15, 20 times the mass of the sun, and you've got all these different layers doing all sorts of nuclear reactions, and then you've got quantum forces involved and gravitational forces, and when the core collapses, you've got all these shock waves reverberating around in tiny fractions of time. We throw the very best supercomputers in the world at this, and they show us interesting, complicated things, and then we look and we find structures which are far too complicated for us to resolve. There's a lot of different groups trying to theoretically study, supernova. This would give us real data. If we can put up a space-based gravity wave interferometer, we should be able to actually detect supernova explosions, not only in our own galaxy, but in other galaxies. And the waves that come off of those will tell us a lot about how those giant stars die, and tell us which group's computer models are correct. They predict a wide variety of different things. That's something we could get out of a really wonderful gravity wave detector. There are two different models that the same group published, and their first calculation said, well, the gravity waves should look like this, the red line. And then after a couple of years, they went to a higher resolution, they added some more physics to there, and then they got something really, really different. That's the blue trace. What this means is we don't know. This is too complicated. This is too messy. This is beyond the resolution of the very best supercomputers in the world. So what that means is we need actual empirical data about what goes on in the heart of the star as it dies. Gravity waves are the only thing that could deliver that. And that's something we need to see. Yeah, there it is, the very best. I mean, there's just so much going on. You've got all the nuclear fusion reactions going in the cores of stars. They fuse elements up to iron. The iron collapses. There's a quantum mechanical pressure from electrons opposing this. It's messy. It's complicated. It's beautiful. It's glorious. And it's an essential process in our universe. If giant stars didn't explode every now and then, well, that's the source of the atoms that make up our bodies. The iron that makes your blood red, the calcium in your bones, the oxygen in your lungs, the carbon in your DNA, all of those atoms originally came from supernova explosions, the explosions of giant stars which took those atoms and spread them across the universe long before the Earth formed. In order to understand these sorts of things, well, that's understanding where we came from. That's extraordinary. So, what does this mean? Well, for 200 years, it looks like Newton has the last word on gravity. Einstein shows that Newton's equations are a beautiful, glorious approximation to something deeper. And so now everybody wonders, well, does Einstein has the last word on gravity? Is gravity done? Is gravity finished? Is Einstein's theory the final, ultimate, true theory of gravity? This is the best test of his theory that we've ever had, and the waves match up with his predictions just beautifully. So that's glorious. If it's an approximation, it's a darn good one, let me tell you that. So Einstein should be smiling. There we go. And the other thing is, and I can tell you about cool things I want to get out of the next generation of gravitational wave detectors. But ultimately, some of the greatest discoveries in astronomy usually come not from the theoretical predicting things, but just from somebody building a new sort of telescope and finding something that nobody guessed or anticipated or thought could ever exist. I mean, the number of discoveries made is by theoretical prediction. We've got a number of those, and then we've got at least as many discoveries made by just building something new, looking at the universe in a new way that nobody'd ever looked at it before, and seeing something wonderful and amazing and shocking and surprising and glorious. That's what I really want to know. Let's put up a space-based gravity wave detector, and then tell me what it shows us after a few years of operation. My guess is we'll see supernovae, and that will be great, and we'll see neutron stars and black holes orbiting around each other, and I want to know, what are the other things we see? The sort of things that nobody would have guessed at beforehand. That's the fun part of the scientific process. Probably the most important discoveries we make with this are going to be things that nobody would anticipate beforehand. Wonderful. Here's a quick summary. So Einstein's general theory of relativity, his theory of gravity, predicts that accelerating masses can give off these gravitational waves that carry energy but are really weak. In the 1970s, Hulson-Taylor found indirect evidence of this through binary pulsar systems. LIGO came online for the first time in 2001, 2010. Did not detect anything. Between 2010 and 2015, they souped it up. They created advanced LIGO. And in 2015 and 2016, the first two verified, carefully tested, measured chirps of gravity waves were discovered, both of them caused by the orbiting, spin-together, spiral in, and merger of pairs of black holes somewhere in a galaxy about 1 billion light years away from us. Thank you very much for your attention.